In 1 billion years, the Earth's oceans begin to boil. The mechanism is the Sun. The same star that has warmed this planet for 4.5 billion years has been brightening the entire time, and the brightening does not stop. In geological terms, the oceans go fast. Within tens of millions of years of the threshold being crossed, every ocean, every river, every lake converts to steam. That is not the worst thing the Sun does to the Earth. The kill sequence does not look like what most people picture. It does not begin with fire. The first death is quiet, slow, and already underway. The last death looks nothing like the Sun you know. We will get there. The Sun is approximately 4.5 billion years old. It formed from the gravitational collapse of a molecular cloud, a cloud of hydrogen and helium gas with trace heavier elements, and ignited nuclear fusion in its core some 4.5 billion years ago. Since then, it has been converting hydrogen atoms into helium atoms via the proton-proton chain, releasing energy as gamma rays that scatter upward through the solar interior for tens of thousands of years before emerging from the surface as light. The Sun has been doing this for longer than complex animal life has existed on Earth. It has approximately 5 billion years of hydrogen fuel remaining in the core, but the burning is not constant. It has been intensifying, slowly and without pause, since the day the Sun ignited. As hydrogen fuses into helium in the core, the helium accumulates. Helium ash. This accumulation changes the composition, density, and opacity of the core material. To maintain the pressure balance that holds the star against its own gravity, the fusion rate must increase slightly as the composition shifts. A slightly faster fusion rate means slightly more energy output. The Sun brightens by approximately 10% every billion years. This figure comes from the standard solar model, the theoretical framework for stellar interiors refined and cross-checked by helioseismology, the science of measuring oscillations inside the Sun, for decades. It is not a guess. 4.5 billion years ago, when the Earth formed, the Sun was producing approximately 70% of the energy it produces today. This creates a well-known problem in planetary science called the faint young sun paradox. The geological record on Earth shows abundant liquid water from the earliest Archean period, meaning the surface was warm enough for oceans, despite the fact that a sun 30% dimmer than today should, by simple calculations, have left the planet frozen. Something compensated. Perhaps a thicker early atmosphere with more greenhouse gases, perhaps higher geothermal heat. The debate has not fully resolved. What matters here is the direction. The Sun started dim, and it has been climbing toward the luminosity that ends life on this planet ever since. In approximately 1 to 1.5 billion years, depending on which atmospheric feedback model is applied, the Sun will have brightened enough to trigger a runaway greenhouse effect on Earth. Planetary scientists define the inner edge of the habitable zone partly by this threshold. The models differ on the precise timeline. What they agree on is the mechanism and the outcome. Water vapor is a greenhouse gas. As solar energy input increases, ocean surface temperatures rise marginally. Marginally higher temperatures increase the rate of ocean evaporation. More water vapor in the atmosphere traps more heat. More heat drives more evaporation. Unlike the moderate greenhouse warming Earth experiences today, which reaches an equilibrium, the runaway version has no equilibrium. It accelerates until the feedbacks have nothing left to feed on. The Atlantic Ocean contains approximately 310 million cubic kilometers of water. The Pacific contains approximately 710 million cubic kilometers. They will not evaporate in years. In geological terms, within tens of millions of years of the feedback beginning, they are gone. The sky fills with superheated vapor. Surface temperatures climb past 100 degrees Celsius and do not stop. Carbon dioxide, baked out of carbonate rocks by the intensifying heat, thickens the atmosphere further. The pressure increases. The temperature increases further. The surface temperature of the Earth at this point would exceed several hundred degrees Celsius. The exact value depends on atmospheric composition models, but the range is consistent across them. Lethal to any biology recognizable today, long before the temperature reaches its peak. Any human being standing on that surface would be killed by the heat in the first seconds. Before the sky turned white with vapor, before any other mechanism had time to act, the sun continues burning hydrogen, getting brighter. It does not register what it has done. The Earth survives the loss of its oceans. It continues to orbit, a scorched, airless rock. The water vapor released into the atmosphere during the runaway process escapes to space through hydrodynamic escape. Ultraviolet radiation from the sun breaks water molecules into hydrogen and oxygen atoms. Hydrogen, too light to be retained by Earth's gravity at the prevailing temperatures, drifts upward and is lost to space. The oxygen that remains reacts with iron-rich surface minerals and silicate rock over millions of years. The sky empties. What is left resembles Venus at its worst. A dense carbon dioxide atmosphere, crushing in pressure. Surface temperatures capable of melting most metals. Weather patterns of any meaningful kind have ceased. Water erosion is gone. Possibly, plate tectonics slows or stops, since water plays a critical role in lubricating the crustal processes that drive it. The geology of the planet stills. For approximately 3.5 to 4 billion years after this point, the Sun remains a main sequence star. It continues brightening. Earth continues orbiting. A dead rock, indistinguishable from any sterile planetary body. If you could observe the Earth from another star at this time, you would see a brownish sphere with a thick, poisonous atmosphere, reflecting no sign of the oceans and organisms that once covered it. This is the pause. 3.5 billion years of orbiting silence. And then, approximately 5 billion years from now, the Sun itself begins to change. The hydrogen in the Sun's core runs out. This does not happen in an instant. Over millions of years, the fusion rate in the core falls as fuel depletes. The energy output drops. The core pressure falls. Gravity contracts the core inward. As the core contracts, it heats further. At a sufficient temperature, hydrogen in a thin shell surrounding the core reignites. Shell hydrogen burning begins. The outer layers of the Sun, receiving an increased energy flux from below, begin to expand. They expand over millions of years. The Sun's radius, currently approximately 700,000 kilometers, grows steadily. In human terms, the expansion takes millions of years. In stellar terms, the process is continuous and unstoppable. Models place the maximum radius at the tip of the red giant branch at between 100 and 256 times the Sun's current radius, depending on how much mass the Sun loses as stellar wind during this phase. Current best estimates from detailed stellar evolution models put the peak at approximately 256 solar radii. At this peak, the Sun's luminosity reaches roughly 2,000 times its current output. Its surface temperature drops from approximately 5,778 Kelvin today to roughly 3,500 Kelvin. The Sun is cooler at its surface, but incomparably larger, and the total energy output is enormous. Mercury is engulfed first, then Venus. Earth is next. Whether Earth is engulfed is genuinely uncertain. The models are divided, and current science cannot settle the question. In 2008, astrophysicists Klaus-Peter Schroeder and Robert Conan Smith published a carefully constructed stellar evolution model for the Sun's red giant phase. Their conclusion: the Sun's outer envelope would extend beyond 1 astronomical unit, which is Earth's current orbital distance, and Earth would be swallowed. The drag from the diffuse outer solar plasma would decelerate Earth. Earth would spiral inward. it would be consumed. But there is a competing effect. As the Sun expands, it loses mass. Red giants shed mass as stellar wind at rates far higher than today's Sun. The Sun will lose roughly half its total mass before it finishes. As the Sun loses mass, its gravitational hold on Earth weakens. Earth's orbit expands outward in response. Some models find that this orbital expansion is sufficient to keep Earth just outside the envelope's reach. Whether engulfment wins or orbital expansion wins
depends on mass loss rates that current models do not constrain precisely. Physics does not have a final answer here. If you encounter a video that tells you definitively what happens to Earth at this point, check whether it acknowledges the uncertainty. This channel does. Both outcomes end the same way. If Earth is engulfed, the planet descends into the Sun's outer layers. There is no atmosphere left to buffer anything. Orbital drag decelerates the planet. Earth spirals inward. As it descends deeper into the stellar envelope, tidal forces increase. The surface temperature reaches tens of thousands of degrees. The rock itself vaporizes. Earth dissolves, atom by atom, mixed into the outer plasma of the star that formed it. No solid remnant persists. The Earth ceases to be a distinct object. If Earth narrowly escapes, a charred remnant orbits a red giant at a marginally wider distance than today. The luminosity falling on it is 2,000 times the current solar output, at a distance only marginally greater than Earth's present orbit. Surface conditions in this scenario are indistinguishable from engulfment in terms of whether any biology or geology survives. The timing of destruction differs, the destination is the same. Physics offers no comfort for what follows. Inside the red giant's contracting core, something else has been accumulating for billions of years. The helium ash from main sequence burning has built up in the core. As the core contracts and heats under the weight of the expanding outer layers, the density and pressure rise until the helium becomes what physicists call degenerate matter. In degenerate matter, pressure depends on quantum mechanics rather than temperature. Normal stellar gas expands when heated, which reduces the pressure and regulates the fusion rate, acting as a thermostat. Degenerate matter does not expand this way. It cannot self-regulate. When the core temperature reaches approximately 100 million Kelvin, helium ignites. Fusion begins in the degenerate core. Because the core cannot expand to absorb the energy, the rising temperature does not stop the process. It accelerates it. The temperature rises faster. Fusion accelerates further. For a matter of seconds, the helium flash releases more energy than the Sun emits over what some models estimate as millions of years. All of it is deposited inside the stellar core. None of it appears at the surface as a flash or explosion. The outer layers absorb and redistribute it. From outside the Sun, nothing dramatic happens. The degenerate conditions in the core are destroyed. The core transitions to stable helium burning. The Sun restructures internally and enters the asymptotic giant branch phase. A second expansion begins, potentially larger than the first. More mass is shed. The Sun burns the last fuel it has. Over a final period of approximately 100,000 years, the Sun expels its remaining outer envelope in a series of pulsations. Roughly half of the Sun's current mass is released into the surrounding space. It forms an expanding shell of ionized gas, glowing from the ultraviolet radiation of the exposed stellar core at the center. Astronomers call this a planetary nebula. The name dates to William Herschel, who in 1785 observed these objects through his telescopes and found that their circular, hazy appearance resembled planetary disks. The name is a historical accident. These shells are the final exhalation of a dying star. The shell expands outward at velocities of roughly 10 to 30 kilometers per second and continues glowing for approximately 10,000 to 20,000 years before it disperses into the interstellar medium, mixing with the diffuse gas between stars, eventually seeding future star formation in deep time. The object remaining at the center is a white dwarf. It contains roughly 50 to 60% of the Sun's original mass, compressed into a sphere approximately the size of Earth. No fusion occurs inside it. The white dwarf is held against its own gravity by electron degeneracy pressure, the same quantum mechanical effect that prevented the helium core from regulating itself during the flash. The surface temperature begins at approximately 100,000 Kelvin. It radiates that heat into space, slowly. Jupiter and Saturn, whose orbits expanded as the Sun lost mass, may persist. They orbit the white dwarf at distances of several astronomical units or more. Cold, dark, frozen giants. Whether their orbits remain dynamically stable over billions of years is not established. They may be the only objects in the system that can still be called planets. Earth, if it survived the red giant phase as a solid remnant, orbits the white dwarf at a slightly wider distance than its current 1 astronomical unit. The energy it receives is a small fraction of what the current Sun delivers. The surface temperature of this Earth would be approximately -270 degrees Celsius, fractionally above absolute zero. Complete silence surrounds the planet. The atmosphere escaped to space long ago, dissociated and lost to the solar wind. The geology has stilled, with no water to drive it. A frozen rock orbited a cooling ember in permanent dark, in a night broken only by the faint glow of a star that is itself in the process of going cold. This is what the Sun becomes 10 billion years after ignition. An Earth-sized sphere of crystallizing carbon and oxygen, radiating heat that no living thing is present to receive. The white dwarf cools. Not quickly. A white dwarf requires timescales of trillions to quadrillions of years to cool to the temperature of the surrounding space. Eventually, at a point in the cosmological future so remote it has no connection to any human scale, the cooling object reaches ambient temperature and stops emitting any radiation of consequence. Astrophysicists call this theoretical endpoint a black dwarf. No black dwarf exists anywhere in the observable universe today. The universe is approximately 13.8 billion years old. No white dwarf has had time to cool to that state. The black dwarf is a prediction permitted by the physics of electron degeneracy and thermodynamics. It has not been observed because we do not live long enough, as a species or as a universe, to see it. The Sun's remnant will become one, in a future that has no language to describe its distance from now. Cold, dark, inert. Carbon and oxygen atoms locked in a crystalline lattice, radiating nothing, in a universe that is itself expanding and cooling. The last stars will have burned out long before this final cooling is complete. The universe will be dark before the Sun's remnant goes fully dark. The sky above you right now contains the Sun 8 light minutes away. The photons arriving at your eyes left the Sun 8 minutes ago. The Sun that is burning at this precise moment will not be visible to you until those photons arrive 8 minutes from now. It has approximately 5 billion years of hydrogen fuel remaining. 5 billion years is a finite number, longer than the Earth has currently existed, almost 10,000 times the age of recorded human civilization. A countdown. The mechanism is already running, has been running since before the first cell divided in the early Archean Ocean. The helium is accumulating in the Sun's core right now, as you watch this. The brightening is already underway. In 1 billion years, the oceans go. In 5 billion years, the star begins its final expansion. And what it leaves behind is a crystal in the dark, that used to be the warmest thing in this corner of the galaxy. Subscribe. The channel does not flinch, and it does not offer you comfort at the end. Every video is one more mechanism, laid out exactly as physics describes it. And if you want what that same physics does at a smaller scale, not in a billion years, but right now, in the first 15 seconds, what space does to a single human body exposed to it, that video is already on the end card. What actually happens to your body in the vacuum of space? Tap it now and keep watching.